Hello all, welcome back to the continuing session of NPTEL lectures on computational process design. So, we have completed design of heat exchanger network and geometric design of reactors. So, now we will move on to a new topic, which is of course connecting both of them, called optimization methods of process design. So, the key summary or the key take home message that we need to consider here is, so in the previous lectures related to the heat exchanger design and the reactor design, we were using algorithmic rules or empirical methods to do the process design. So, now what we are going to do from here onwards, in fact the couple of classes from here, we use the principles of optimization, which of course you have learned in the one of your previous lectures, okay, and trying to integrate them in the process design, in the realm of process design. The idea here is that optimization methods are very powerful, such that you don't have to go ahead and manually compute any relationship or the optimal value or the ideal way of connecting certain networks. So, it would be all done by the optimizer or optimization as the solution of the optimization problem. The only thing that you have to do here is form the optimization problem accurately. So, this particular class and of course coming classes, we would try to see how this can be achieved. So, again the content of this lectures are predominantly coming from our reference one, Bigler and Grossman and Westerberg, systematic methods of chemical process design. So, this is considered to be a classical book that actually uses the principle of optimization for chemical process design. So, the contents of this lectures are mostly coming from that reference book as we have discussed. So, let us move on. So, maybe just to get a hang on what we have done maybe in last 3-4 classes, we will just do a quick recap. So, we have done the first class was all about heat transfer and heat exchanger. We can see that there are various modes of heat transfer, okay, conduction, convection, and of course radiation, okay. So, what we are going to do here, we are trying to recap them. Conduction is of course heat transfer through a solid material through molecular vibration, and the governing rule here is the Fourier law of heat conduction. And convection is nothing but the heat transfer between a solid surface and a moving fluid or liquid or gas. And here the governing equation is what we call it as the Newton law of cooling, which talks about Q is equal to H A delta T, where Q is the heat transfer, H is what we call as the convective heat transfer coefficient, A is the area, and L delta T is the temperature difference. And the third method of heat transfer is radiation, which is of course governed by the fundamental principle of Stephen Boltzmann law. Okay, heat transfer through happening through electromagnetic waves if we consider the radiation form of heat transfer. So, here the heat transfer of course is a function of uh, area and temperature to the power 4, and there are two other parameters which we call it as epsilon, which is the emissivity, and sigma, which is called as the Stephen Boltzmann's constant. Then we did about heat exchangers. So, heat exchangers are the process devices that designed to efficiently transfer heat from a hot fluid to a cold fluid. The parameters affecting the design includes the inlet and outlet temperature, the flow rate of the hot and cold fluid, and physical properties such as density, viscosity, conductivity, and specific heat. So, they all directly involved in heat transfer calculation. That is why these are important. The next important variable that we have learned is heat duty and something known as logarithmic mean temperature and heat transfer coefficient, which is used to determine the uh, total heat transfer area and the flow and the type of flow management. So, which is the required flow that you would like to, which is the cross flow, counter flow, and parallel flow, and so on and so forth. So then we went ahead and looked at heat exchanger networks. So heat exchanger networks is a array of network that helps you to recover the maximum heat from a streams of a set of streams of hot and cold fluid. So there we have to pair the process streams by using what we call it as a CP value, which is the heat capacity ratio, and we also need to find out what is the delta T minimum. So that is the key thing in the network design. And then in that direction we learned about composite curves. Okay, we also learned about what we call it as the pinch analysis and also the pinch point. So pinch point is at pinch point, which is the critical temperature difference. It is essential for setting the energy target to avoid inefficiencies. And we also learned about threshold problems when utility requirement disappear at certain condition. And we also talked about stream splitting using CP values. Then we learned about an algorithm which is known as problem table algorithm, which is a method of calculating the energy and the targets without graphical construction. So one standard way to do all of this by looking at the profiles of hot fluid and the cold fluid, but it may not be easy to visualize them. So how to do it in a mathematical way? So an algorithmic way that helps you to find out, which is the problem table algorithm. Then we also speak about how to size reactors. Basically geometric way of sizing the reactors, which we talk about, wherein we talked about plug flow reactor, CSTR, recycle, and also looked at a concept known as attainable region. So attainable region, identification of the attainable region typically helps in obtain the feasible operating condition, considering the constraints and other operating issues. So now we have done all of this by means of certain rules or heuristics. So this particular lecture, which is actually trying to solve the similar problem or maybe the same problem using the principles of optimization. Okay. So see, you may consider this as a way of automating the algorithmic procedure that we have learned here by means of the principles of optimization that we have learned few lectures before. So let's look at how to pose a heat exchanger network design as an optimization problem. So in posing heat exchanger network as an optimization problem, we'll have to actually identify what we know and what we are interested to find out. So based on what we know, delta T min or a given delta T min, we can calculate the exact amount of minimum utility consumption before developing the network structure. And based on the pinch technique, a full network can be divided into subnetwork. Okay. Above pinch, below pinch, and we do the analysis individually and we combine them. That's what we have learned in the couple of lectures back. Then what we do is we estimate the total area of the heat exchanger. So if total area of the heat exchanger is computed, then you can actually design the heat exchanger appropriately. Then what we learned there, or what we know, that the minimum number of units, how do we compute the minimum number of units, how to connect minimum number of units. You really don't want to have too many kind of interaction between hot fluids and cold fluid. We need to operate them optimally so that minimum number of taps can be provided. It is eventually based on the fact that if there are more and more connection, it is in real plant, it is reflecting as more or more piping. Okay, so any additional piping, which essentially means what? So it is, so you need to have more space, we need to have more cost in terms of the piping, and also of course maintenance. So this is just to optimize the way we want to. So now, so what were the challenges there? So we know the algorithm, we know how by problem table method we can do all of this, but the challenges were that we did not address at that point, we were not having an explicit procedure for deriving the heat exchanger network. We have an algorithm that of course we can follow, which essentially means a lot of manual calculation has to be done. And sometimes you need to do this trial and error for matching and splitting of the streams. So sometimes your streams will not be balanced. So we'll have to try couple of options to see how you can connect between the streams to achieve the targets of utility consumption, so that minimum number of units are connecting to each other, and of course to attain minimum number of total area, because the more the total area essentially means that the more heat exchanger size, again more cost. So now in this particular case, what we are going to do is we formulate this problem, heat exchanger network, as an optimization problem with several constraints. So we cannot violate such constraints. So we have learned about optimization and the constraints before. So now let us see how a physical problem can be formulated, especially the heat exchanger design problem can be formulated as a problem of optimization. See, and what would be our main aim? We should have minimum utility cost. We are not interested in spending more utility, and we should also have minimum number of unit, and we also have minimum investment cost. So the total investment cost should be minimum, total number of units in the plant should be minimum, okay, and of course the utility cost, which helps you to do this heat transfer, the additional heat transfer, should also be minimum. So we now in the next few slides we tend to pose these three objectives. Sometimes we probably need to match all of them, then we solve that this problem has to be solved in a multi-objective optimization framework. Of course, we are not going there, but just to give you an idea that all of them has to be solved simultaneously, then it's become a multi-objective optimization problem. Fine. And if you are solving each of them individually, okay, then they are single objective optimization problem. So another way to do this is maybe you consider one objective, okay, as the primary objective and other two as constraints. So you say that you have minimum, you cannot have more than X number of process unit, you cannot have more than X number of X amount of investing, Y amount of investing cost, keeping the minimum utility cost minimizing. So there are multiple ways to pose it, but at the moment what we are going to do is we try to formulate this problem individually, so that so that we can look into the details how we are reformulating it. And as I told, one can also go solve them as an individual optimization problem or a multi-objective optimization problem. So now let's look at the problem again. So this is the same streams that we have learned before. Okay, so you have two hot streams and two cold streams as we see here. Okay, the Cp value of that is shown in the table, and the temperature of the H1 comes inside and goes out as 120, H2 comes inside as 320 degrees C and go outside with 120 degrees C, while the cold one 160 degrees C, the temperature of that is increased to 400, and C3, okay, which is the second cold stream, goes from 100 to 250. And the utilities are available. So there are two utilities. So a hot utility is of course the steam, available at 500 degrees C, and cooling water available at 20 to 30 degrees C. So what we are interested in now, minimizing the utility cost. So we don't wanted to use, or we don't wanted to take utility too much of utility energy in doing this entire heat exchanger design. So now let's look at the diagram. This also we have learned it before. This is, we have partition done into the temperature intervals as we see in over here. Okay, you can see that uh, the temperatures, uh, we can see that it would eventually result in 4 intervals. Okay, so this procedure of we have learned when we did the pinch design, and here also we show the type of pairing. So we see that H1 is now H1, which is going coming inside as 400 and goes outside as 120. H2 is comes inside as 340, goes outside as 120, and The same for and similar inferences for the cold stream as well. Comes inside as uh, possibly at 160 and goes outside at 400, and comes inside as 100 and goes inside at 250. And this part of the table, specifically talk about the heat contents. So now let us visualize this in the form of a network. So this network design is what we have learned to how to design it in the when we talk about the network of heat exchangers. So we have 4 units. So QS would be the additional heat utility that we need to add, and QW is the additional cooling utility that we need to put in, and you have 4 such stages or 4 such intervals. Okay, and this is exactly corresponding to what we have drawn here. Okay, so the first part is about this particular interval, this is second interval, this is third interval, and this is fourth. So you can see over here that in the first interval, you can see this is the direction of the temperature decrease and this is the direction of temperature increase, and you have 2 hot streams and 2 cold streams, of course, and they were aligned to match everything. So now, let us write the balance across each of these intervals. So let us look at the case 1. So R1 is going out, okay, 30 here, and whatever we are coming in is QS. So R1 plus 30, which is the what you call the difference in terms of the heat utility, R1 plus 30, which is equal to QS. In fact, the heat load you can see over here. See the heat contents megawatt. So this would be 30, 60, 90, all this information. Whatever we have defined is what we are showing as a schematic over here. So this would be the first equation. Let's look at second. So second, so yeah, so R2, okay, R2 plus 90, fine, which is equal to R1, okay, plus 60. So this second equation is also getting a tick mark here. And look at R3, which is look at the interval 3, R3, okay, R3 is going out, and so there are 2. So if you look over here, so okay, you have 2 heat connection. So heat contents you will have to add 2 for the cold and 2 for the hot. Okay. So if you see over here, so R3 plus 117 plus 240, which will be 357 here, again coming inside as R2, and you have 2 connections from hot, 160 and 320, that will be 480. And finally your interval 4, wherein you have QW plus 78 on one side and R3 plus 120 plus 60, 180. So this is the balance that we need to achieve. So and what we are interested in now, so this is the balance that we need to achieve, okay, and we are interested in minimizing the QS, which is the hot utility, and QW, which is the cold utility. So then we formulate this as an optimization problem, wherein you need to minimize a variable z, which is a summation of QS and QW, which is which is hot and cold utility respectively, such that these balances are maintained. And also we need to understand that all these residual heats R1, R2, R3 should be definitely greater than 0, and of course the utilities QS and QW is also greater than 0. So this is actually forms what we learned earlier as a linear program. So when we solve this problem, okay, then we will get what is the QS and QW optimally that we need to get. So you can say that this would result in, so we are skipping the solution. The method of solution is something that you learned earlier, okay, and you may solve it and eventually we get. So, the emphasis here is how to formulate the problem. So, solution strategy is something that you have learned in one of your earlier classes. So, you will get QS as 60 and QW as 225. And once we get that, okay, so then the rest R1 to R4, R3 could be easily found out. So you substitute Q1 and QW over here, then you will get the corresponding R1, R2, R3. And once we do that, we will see that, so magically R2 turning to 0, which essentially means that, okay, so this is the R2, correct. So the pinch is happening, so somewhere between this area, which is between 340 to 320. So there could be multiple pinch points as well, which we can't avoid. So this is one nice way of formulating the entire problem in terms of optimization. So we will move on. So now what we are interested in, as we have illustrated one example, so we will now move on and try to formalize this by means of a standard optimization procedure. So let's go and try to make a standard linear programming model for minimizing the utility. So what we see on the right hand side is the schematic of an interval. So this interval corresponding to one of this interval what we have seen here, okay. So we just pick one of the intervals, okay, and we can see that there are multiple streams coming in, multiple streams going out. Let's understand all of this, okay. A residual Rk minus 1 is the so the residual that is coming from the previous interval, and Rk is the residual that is going out. When you have hot processors one side and cold processors on the other side, okay, and look at what are those variable QHIK. So QHIK essentially means the heat content of the hot stream I, okay, and QSM. What is QSM? Is the heat load of utility M, okay, and now look at the cold process QJKC. QJKC is the heat content of the cold streams J in the interval K. Both of this, so we are all speaking about, specifically speaking about this interval K. So everywhere you see that an index K would be attributed. Q and W, okay. Similarly, Q and W, which is the heat load of cold utility in N. So now we can do the balance as we have done in over there, and so see we have to match this constraint. So before we look at the objective, let us match the constraints, okay. Rk minus Rk minus Rk minus Rk minus 1, which is the first term, okay, which is Qnw minus Qms, which is the second term, and this of course and the third would be Qjkc minus QHIK, which is taken to the right hand side. So the signs got changed, therefore it is QHIK minus QCGK, and we have put summation here and there everywhere, because if there could be multiple such streams. So if there are multiple such hot streams and hot utilities, cold streams and cold utilities, you then lump together by means of the summation and write the balance, and you have such K such intervals, capital K such intervals, okay. And now what are we interested in? We are interested in minimizing the utility cost. So now let us define two variables, okay, which is Cm, which is the unit cost of hot utility M, and Cn, which is the unit cost of cold utility N, okay. Then we have Qms, which is the heat load of hot utility M, and Qnw, which is the heat load of cold utility N. Now fine. And what are we interested here? Again, to minimize the utility. So we define the variable here as summation of Cm times Qsm sigma over all possible such streams plus Cn times Qnw sigma of all such streams. Fine. And this is the objective, this is the constraint, which is the balance not yet over, okay. And we all know that all the Q's, the utility numbers, which is QNS plus QNW should be greater than or equal to 0. Okay, and also the RK, which is the heat residual in exiting the interval K, will also be greater than or equal to 0. And other constraint is, you can see that the first utility here, okay, so your R1 to RK, so your heat residual number starts at R1. So you look at this example for a unit having for a system having 4 unit, the heat the residual heat number, so start with R1 and ends at R3. There is nothing like R0, R0 become QS, and nothing like R4, R4 become QW. So when we write this equation in a general fashion, we also have to acknowledge the fact that R0, there is no R0, so R0 is equal to 0. There is no RK, so RK will be equal to 0. R0, in fact, R0 so your numbers only start from R1 to RK minus 1. So if you have this standard optimization framework for any system with an interval K, okay, so you can see all these equations are ranging from K is equal to 1 to K minus 1, okay, here K is equal to 1 to K. So you have so many equations and this many so many equations which forms the constraints and the objective. You formulate this problem appropriately. This is the appropriately formulated problem. Okay, you feed in that to the optimizer, and optimizer would steadily give you the values of unit cost of hot utility and cold utility, and the residual heat, and also the and the correspondingly you can find out Q, the heat load of hot utility and cold utility. So the procedure is now, so see the difference that we need to understand here. Previously the procedure was algorithmic and trial and error involved. So here we have changed the problem into more structured and optimizer, and an optimization problem will take care of the solution of it. Okay, so now we will move on. So now we will look at the problem of minimum number of units. Okay, in minimum number of units, what we have to do is, so we are interested in only having a minimum number of connections, so that you have your network is fairly more compact. So we have to, what we are interested in. Okay, so we will define certain variables like previously. Okay, so each subnetwork is based on the network separated by pinch points. Each subnet, so let's consider a subnetwork Q. Each subnetwork Q will then have an associated set of temperature intervals. So that we have seen previously. So for any subnetwork Q, we are defining a variable called as yiq become 1 if the hot stream I exchange heat with the cold stream J, 0 if hot stream I don't exchange with the cold stream J. So we are looking for, so if there is so hot stream 1 exchange heat with cold stream J essentially means that there is a connection, or there is a so you are bringing a heat exchanger over the hot stream I don't exchange with cold stream J essentially means that there is no connection, there is no unit involved. Fine. And you can see, so you can see that when we sum all such cases, summation of qij, if there are zeros, they won't come into the picture. If there are ones, it will be just added up. So our objective here is to sum up. So to minimize the number of unit, the summation of yij over q should be as small as possible. So if the smaller the number, or smaller the value of the summation, essentially mean that the times which the hot stream exchange with the cold stream are minimal, which essentially mean that the entire network size is smaller. So let's look at the balances over here again. So this is an example. So we are interested in RIK minus RIK minus 1. So again over here, okay, and QIJK minus Qijk minus Qhijk, and when we take this Qhik into the right hand side, this is the structure. Okay, not over, and sigma of all Qijk becomes Qcjk. Fine. So all the variables have been defined appropriately. For instance, Qijk is the heat exchange between hot stream I and the cold stream J at an interval K. So this is all the analysis is performed at an interval K. So that's why index K coming into the picture. Fine. Uij, we'll speak about that. Okay. So Uij, we will define the smallest heat content of two streams at a later time, and Qhik, and Qcjk heat content of the whole hot stream I and the cold stream J in the interval K. This is we have previously defined, and and so on and so forth. And here also we see that your Rj's, Rijk and Qijk should be greater than or equal to 0. Okay. So what we see over here is that, so when there is no connection, essentially mean that Yijk will be equal to 0. So which essentially mean that heat transferred through that also will be 0. So total heat, so when we have an additional balance, so to summation of all Qijk, which is the heat exchange between hot stream I and the cold stream J at an interval K, minus Uij, which is the smallest heat content of two streams times Yqij will be less than or equal to 0. Why? Because so let's say if there are all connections available, this would be a perfect balance. It will, instead of this inequality, this become inequality. But otherwise, what we would see over here is that uh, so this additional constraints would play a role in keeping the things balanced. So this again, so this I would also like to speak about the problem structure of this. So again, this is, you see that there are integer variables involved in here. So 0, 1, 0 and 1 is an integer variable, but all the other variables are continuous. And all the summations can also be translated as linear equations or even linear inequalities. So the point here is that, okay, so this problem would contain integer variable in addition to the continuous variable in a linear programming setting. So this would, for this particular structure of the problem is typically called as mixed integer linear programming problem. Okay, of course you have learned about how to solve, or rather what is the key thing in mixed integer programming in one of your earlier classes. So now let's look at the third uh, objective here. So the minimization of the investment cost. So the investment cost typically related to the function of the area of the heat exchanger. Why? Because if there are more area, which essentially means that your heat exchanger should be high. So your a bigger heat exchanger will cost than a smaller heat exchanger. So, so this is the, so investment we typically depending upon the area, and which in turn area is essentially depending upon the what we call it as the logarithmic mean temperature differences. So how do we define? So let a power b. So let's assume that this function of that relates between the function that relates area to the cost is a power b, where b is a constant, and you have n such units, sigma ci ai power b or aib. We have to sum it over n number of units. Okay, and now you can see that your q which is of course the heat transferred, is UA delta TLM. So this part is the delta TLM and this is the AI. So now you can rewrite your AI as QI minus, okay, UI times delta TLM. So the minimization of the cost we can write in terms of the delta TLM power B. And the constraints, you can have certain constraints here. You can have the minimum the pressure drop limitation, minimum temperature approach, and other operational design constraints specific to the network that is being designed. So, this is the what you call the third objective. So, we talked about three objective: minimization of investment cost, minimum number of units, and minimum utility costs. So, as I told, this can be individually minimized, okay, or minimized together in a multi-objective framework. Of course, that part is we are just leaving that part for now. So now let's speak about, so similar to the way we have designed heat exchanger using optimization, the reactor networks can also be synthesized using optimization. Here we will not go into the details, okay. You can definitely refer to the textbook for more details. So we will just showcase one example how we could just utilize this principle when we uh, and so in the same fashion we can implement the same. So just to recap, so we have learned about attainable region. So attainable region is a concept that is used to define the feasible operational space of a reactor constrained by various inputs such as raw materials, energy, and output as desired products. For complex reaction systems representing a full range of possible reactor behaviors, it is it is definitely challenging and requires considering multiple dimensions and external parameters for such design. So, we can just replace this entire what you call heuristic based design by means of optimization tools. So, we in that case you may have to go for uh, nonlinear programming principles or mixed integer nonlinear programming principle, considering the fact that most of the reactor equations be potentially nonlinear in nature. Okay. And another motivation for doing such an operation for doing this particular approach is because when the operator condition changes, okay, you cannot again do a trial and error approach to find out what is the new attainable region, what is the new process parameter, and so on and so forth. But if you have an optimization framework available, it would be, you only need to resolve the optimization problem in a computational setting. It will be much faster. And as a result, this would help in avoiding problems that comes with high dimensional systems. So high dimensional system may have many such variables or many such units, and your ability in dealing with all of them in a pen and paper traditional conventional way would be very difficult. Okay. And we can also move away from the concept of ideal reactors in when we define using optimization, because you can also have the, if the reactor model is available or a mix of reactor model is available, use that particular model in the optimization framework to obtain the solution. And also you can also combine the concept of attainable region with this optimization techniques for better explore the reaction what you call to better explore the potential solutions that have dual capabilities. So maybe we'll just look at some insights on optimization based method for reactor synthesis. Okay, so what are we here? The objective here is to maximize the production of desired product, okay, or to minimize the total cost, or including both and operational and capital cost. The function could take in various form, okay. So maximize the yield, maximize the selectivity. In most cases, selectivity is considered as an important variable because you have multiple outputs, and how your desired product is superiorly produced compared to the other byproducts. Or you can have a function that actually takes care both yield and selectivity. For instance, it could be a summation, it could be a function, and so on and so forth. And of course, we have to minimize the cost. And what are the cost here? Capital and operating cost. And the variables that we can typically manipulate here or control, or maybe you can change here, which we call it as the decision variable in the optimization problem, that include molar flow rate, reaction rate by manipulating the temperature, okay, volume of the reactor, temperature, pressure, and of course the output, the desired output would be either selectivity or yield. So now let's see the constraints that we have to deal with there. So there are various constraints. So this is whatever we have learned here is an objective. So look at the constraints. Okay, there would be material balance, which is like input in accumulation is equal to inlet minus output plus generation minus consumption, as we have seen in the one previous cases. Okay, dxi by dt is equal to fn f in I, f out I plus sigma of Rij Vk, where Vk is the volume and and Rji is the reaction rate. And of course, heat balances are there. Qk, which is heat of the reaction produced, heat of mixing, and heat of heating bar cooling. And reaction kinetics is a function of temperature and concentration, pressure, so on and so forth. In addition to that, you will have what you call constraints on operations. For instance, volume of the reactor, you can have a minimum volume and a maximum volume, because you cannot make a reactor that is infinitely big. The temperature that you can handle, minimum temperature to maximum temperature, smaller temperature might not favor reaction, higher temperature might have an issue in a runaway and hot spots, and the pressure also, minimum pressure might not be sufficient to drive the reaction. Maximum pressure may not be withstandable in a reactor setting, and you can always demand for certain minimum selectivity and a minimum yield. So this entire problem would be recasted in an optimization setting. It would typically become a nonlinear program due to the function. So see, you can also see over here the rate comes into the picture. So rate expression is a nonlinear expression. You see exponentials over there. So here we are in, so the entire problem become a nonlinear program. So now we will show a small example on how to formulate such an optimization from a segregated flow isothermal reactor. So, what is a segregated model of isothermal reactor? So, for isothermal reactor system, initial symbol representation is a segregated flow model, where the molecules at the same age, preferably mixed, and mixing will exit, and after mixing only occurs at the reactor exit. The optimal network can be synthesized by the optimal residence time distribution function, which is f of t, which governs the mixing and the reaction process. In the segregated form models, molecules of different ages typically do not mix in the reactor. Okay, they react according to a specific rate law, leading to the differential equation representing the concentration over time. The rate of change of concentration for segregated flow, which is x dx segregated by dt, is equal to the reaction rate, and x exit, the exit age conversion. So the exit conversion would be integral t naught to t max f of t x seg time x seg of t dt, and integral of t naught to t max t times f of t dt would give you tau, which is the mean residence time. And of course, you can have that normalized. Integral t naught to t max f of t is equal to 1, which is RTD. This is the normalized structure, which behaves like a probability distribution, so that the integral will be so that this integral will be always 1. So let's look at the optimization framework for an isothermal reactor. The isothermal formulation of the might involve maximizing a certain performance index. So the performance index J would typically the conversion is a function of typically the conversion and residence time, as we saw here. Maximize performance index, which is which we can define as a function of exit exit and tau. Okay, and we and what we are interested here. Okay, and what we saw over here is that these are the constraints. So these are the constraints that we have learned. So this is x dx sec by dt times r x sec is one relation that you need to obey, and you have an initial concentration of x segregation, and x exit would be t naught to t max f t x sec dt, and these are the resident times expression. So everything has to be honored, and this is how an what you call segregated flow reactor operates. So let's speak little bit more about on the performance index. The performance index in the segregated folder is maximized by varying ft, which is which is reflected in the objective. So you typically change ft, which is the function. The objective function j can be any function of x exit and tau as per choice by the designer. If the dimensionless feed concentration x naught is pre-specified, x at t become independent of ft, okay, and other differential equation can be solved by means of separately from RTD equations. When x is determined, ft can be found, which might satisfy a set of constraints that we have learned earlier. So now let's move on to the so how do we extend this in computing the attainable region. So attainable region also can be found by means of optimization. In that, what we have to do in here, the optimization process, we have to do an optimization process where the optimization process begins with an initial attainable region, which we have initially found out by means of possibly by means of geometric methods as before, and that is a candidate region for the larger synthesis. If the objective function j, so you have to of course need to have a performance matrix which is objective function j is concave. The optimization formulation provide globally optimal network within the segregated flow models. This idea of how a concave function gives you a globally optimal solution you have learned earlier in your optimization lectures. For complex system, the attainable region may not be fully captured by segregated flow model. In such cases, additional optimization formulations are needed to extend attainable region beyond what is described by the simple segregated flow model. Below are the steps here. So first we have to evaluate the current attainable region. Then we have to look at the gaps. For instance, is there a way to improve purity? Is there a way to attain better yield? If that is the case, you can consider adding more reactors. If the current setup is not sufficient, adding more reactors. This could be like a PFR or a CSTR or changing the size, okay, or you can also change the operating condition. If that is done, then you can again update the attainable region. So when we add a new reactor or we change the size of the reactor, the new attainable region is found. So because it's a geometry, so your the attainable region size would increase, or maybe shape would change if you add the additional reactor, and this process would keep on changing. Though, so when we add the reactor, when we are typically moving towards the air close to our desired attainable region, close to our desired performance targets. Once that is done, we can keep on iterating with it, keep on adding more reactors, adjusting the size until no further improvement can be found. And the final candidate when the off point for the reactor network synthesis is obtained, which should be represent the optimal configuration of the reactor network, satisfying the list of objectives that we have specified. So this procedure typically done in iterative fashion, where when you start with an attainable region, okay, then once you have an attainable region available, then we can evaluate it, then identify the gaps, add more reactors, again update the attainable region iteratively until you find the desired objective. So we'll close this class by just connecting whatever you have learned with operability and process control. This is what would be the extended session that we are going to have in the next class. So we speak about 2-3 points here. So what is operability? Operability in process design refers to the fundamental principle of ensuring a process that can be operated safely, efficiently, and reliably. It encompasses various aspects, include safety measures, equipment reliability, ease of maintenance, and ability to handle variations such as feed quality and operating conditions. Operability consideration must be integrated in the initial design phase in case of retrofitting or during the modification of the process. If there is any changes, all these operability constraints, since you can add as a constraint in an optimization problem. So in addition to these constraints that is listed over here, you can also add the operability constraint, so that you ultimately meet with the measures of safety, reliability, and what you call as the sustainability. So, then the next aspect is control. Both are tightly correlated. So, control is closely linked to operability, which is essential for maintaining the desired performance. The process control designs involve feedback and automation that regulate key process variables such as temperature, pressure, and so on and so forth. Effective control ensures process stability, consistency, and product quality, and the ability of the system to respond to any changes. In context of process design, control strategies are tailored to the specific objectives of the process that involves retrofitting an existing system or designing a new one. So, in computational process design, we do not see the operation and control is different from the design. So, we talk about everything in a cohesive manner. So, when we move about, so see, we have talked about an optimization based method of process design, which would be now tightly integrated with the conditions of operability, while design and control we tightly try to achieve the desired goal. So, when we design, so design and operation are not typically independent. Okay, so in fact both of them has to be joined hand together when we need to have a tighter control, a reliable and safe operation, achieving the best productivity with a with minimum cost. With this, we will just summarize the lecture. What we have learned today is about heat exchanger network optimization, then reactor network synthesis, and we also talked about how attainable regions can be iteratively developed. Fine, and also talked about how operability and process control are tightly integrated with the design. They are not together. In the conventional approach, you kind to see them together, but when we put together an holistic view, design and operation are not independent. You have to, when we design, we should account for all uncertain cases, and while operation, you should be able to handle all of them together. With this, I think we would like to close today's lecture, and we continue this optimization based design, wherein we talk about little bit of scheduling and other related process flexible operation and scheduling in the coming class. Thank you and see you soon. Thank you.